Everyone, I am Shiv Prakash, Research Scholar, Department of Electrical Engineering, IIT BHU. Let's start the session. Okay. I have taken question of first from a buck converter. A DC-DC converter shown in figure is switched at 100 kilohertz. The value of inductance is 2 microhenry. The duty cycle of operation of MOSFET is 0.5. Assume the inductor current to be continuous. There are two types of continuity, discontinuous and continuous inductor current. Is depend on the value of inductance. The value of output capacitor is C required to keep the peak to peak output voltage ripple as 1% of the average output voltage, and also would be the capacitor value. The converter is working.
Sir?
Yeah.
So can you show the question once? Okay, sir.
There are three conditions: continuous and discontinuous, and the critical condition of inductor current. Discontinuous conduction mode, it means inductor current or inductor current is discontinuous. Like a first one, IL continuous means this one like that. This is the total time period T. This one is a dt on time period. This one is the boundary condition. This one continuous conduction mode. This one boundary condition, critical conduction mode. Third one discontinuous conduction, like this type of form. IL 0 dt and another taken like a beta t, and total time period is t. Dt time period is on time, and dt to bt beta t is time period for off time of switch off, and remaining is when conductor current is 0. What will the condition that any converter goes to the discontinuous or continuous condition mode? For buck converter operation, take like a boundary condition. So the IL dt t. Then what will be the average of ideal inductor current? Like this one, that one, del of this one, IL, and the total ripple is del ripple current delta IL. Delta IL can be expressed as IL expressed as delta IL divided by 2, half of this one. If a boundary condition is given at a boundary condition, means a critical condition, average current of inductor current is delta IL by 2, half of the ripple current. IL in a buck converter, IL same is I naught, same current flow like this one. This IL average current, and this one average output current. Average current at average current flow through the capacitor is 0. That's why average inductor current same as the output current of converter, buck converter. Then V naught can be expressed as V naught by R, and V naught is replaced as dVs. and you can put here dvs by r. Delta IL same as when switch is on, Vs minus V naught appears on this into dt times, can written as Fl. Could you get V naught as a dVs, then you can common Vs 1 minus d into d divided by Fl. Sorry, this one is 2 delta L by 2, then this one is 2 Fl. Vs cancel out. 2 Fl by R is equal to 1 minus d. This is the boundary condition of buck converter. If this one, suppose as a K and this one is a Kc, critical condition. If K should be greater than Kc, it means a continuous conduction mode. This value is greater than 1 minus d, means continuous conduction. The converter work in continuous conduction. And if K is same as 1 minus d, is the boundary condition, a critical condition mode. If K is greater less than Kcr, critical K, this denoted as the discontinuous conduction of a buck converter. This one is a different for different converter. A buck converter is 1 minus d. In the whole of this frequency is resistance and maximum time there inductance and the frequency are more affected to the continuous or discontinuous conduction. Then continuous conduction, current flow like this. IL flow, switch is turn on, and this one is turn off time. The remaining one switch current is off. This one it zoom as a another time period is beta t. This one is a t. In this time period, if you take as a VL out inductor voltage from this one, the switch is on, then VL, Vs minus V output appears on the inductor voltage, like that. But when switch is on, off, only minus of output voltage appears on the inductor. This diode working on off time, and this VL is same as minus of output voltage. And remaining when the current is 0, it means inductor voltage also 0, no current flow, and voltage no voltage drop across the conductor. Then on volts, if you apply a volt a second balance equation, you can find the output voltage in discontinuous conduction mode. Volt second is says that voltage, iris voltage of the inductor is 0. It means on time voltage dt plus off time voltage 1 minus dt plus remaining time this one is in discontinuous, not at off time only beta minus dt plus remaining t minus beta t, means 1 minus beta into Vr is equal to 0, total time period. This one, this VL when switch is on, Vs minus V0 into D, T cancel out all of them. And when switch is off, only V0 appears on this. You can take as a beta minus D, and remaining time voltage is 0. Inductor voltage 0, and this one is simply 0. Then this one dVs minus dV0 minus beta V0 plus dV0 is equal to 0. V0 cancel out. V0 is equal to dVs divided by beta. This was the output voltage buck converter when in discontinuous conduction mode. You can observe this one betas in between 0 to 1, maximum at minimum you can say at the D duty cycle, and maximum is the time period in continuous. It means if you divide any quantity less than a 1, then the whole quantity is greater than this original quantity. It means if you take a beta as like 0.6, 0.8 something, then whole up output voltage is greater than the dVs. Even you can say that output voltage in continuous conduction mode should be less than V output in discontinuous conduction mode. It means discontinuous conduction mode output voltage is greater than the continuous conduction mode. You can observe from here this time period negative voltage appears only for this one, but in continuous conduction mode total negative voltage appears here, this one full time, and that is the negative to the positive voltage. That's why output voltage is less than in continuous conduction mode.
Sir, beta minus D, how did you get?
This time period Vt minus beta t minus dt is the time period of off time period. The switch is off. This term.
Okay, and in the previous case you got 2, right? How did you get 2?
This one,
In the 2FL, 2FL, yes.
yeah.
2FL, just go down. 2FL.
This one when in boundary condition. At a boundary condition, not about discontinuous condition. There is a in boundary condition from this form. The inductor
Okay.
current average. This one is the average inductor current. Average inductor current is a half of the ripple current. If this one is not a at a 0, starting from 0, that means this equation is not true. Only this one only to true when the current is starting from 0 and ending maximum. For this one a voltage when dt to beta t is minus V0 is appears here. Remaining is voltage is 0. The output voltage is dVs divided by beta. Comes into the questions. I was asking about it. Assume the inductor current to be continuous. Here, give the continuous conduction mode, not a discontinuous conduction. And duty ratio is given 0.5. Inductor also is given 2 microhenry. And a peak to peak output ripple is given delta Vc is 1%. Know about the delta Vc is delta Vc means delta Q change in the charges near In charge condition or discharge condition, changing the charges divided by C. So like a half and delta IL by 2 into T by 2. It's a average current in charging condition. Can take in a discharging condition also. So delta IL means when switch is on period. You take this one ripple 0 to here. In continuous conduction mode, take this one minimum to maximum, I minimum to I maximum. In this period, Vs minus V naught of Ps on the inductor, and this slope is Vd voltage divided by L into T. Same as if you take average in delta IL, Vs minus V naught into time is dt time divided by 8f, this one delta IL by FL, sorry, frequency 8C LC. This one T and this one delta IL is of this one into T. You can say T square, delta Vc is equal to Vs minus V naught into D T square divided by 8 LC. It means Vs minus V naught. You can take a V naught is a dVs, then you can take a common Vs 1 minus D into D divided by T. You can say like F square 8f square LC. You want to calculate capacitor, then you can written like that 8 f square L into delta Vc. Delta Vc is given 1% of output voltage V naught, you can say 0.01 V naught, and dVs you can say is V naught in the buck converter. V naught cancel out, all value is given, frequency is given, inductor is given, duty cycle is given, you can calculate it. Yeah, approximately 12.5 microfarad. Second question taken is from boost converter. The output voltage of a DC converter shown in the figure is to be regulated at 48 volt by PWM technique. The input voltage can vary between 20 to 30 volt. This one output voltage is 48 volt, constant 40 volt, 8 volt, because it is regulated by the PWM technique. It means your controller is used to maintain the output voltage. The load resistance is 12 ohm. The converter is operated at 100 kHz switching frequency. The value of inductance required to limit the maximum allowable inductor current ripple to 10% of average inductor current. This one boost converter is given. You can analyze the converter from in on time, off time. If switch is on, it means 0 to dt time period. This switch is on, then this voltage VL same as V in, VL is equal to V in, and here current flow like that. When switch is off, sorry, so when switch is on, then capacitor deliver the power to the output, total power. Means IC is same as the minus of I naught. This one I naught direction, and this one IC direction, this one I naught direction. And IC is in minus of I naught. To maintain the constant current, I assume as the voltage and output is a constant. When switch is off, it means this is off. The source and inductor both supply to the load like that. That time VL is equal to Vs minus of V naught. And that time inductor capacitor current is IL, this one current flow IL minus of output current. I have two equations, first and second. Can apply a volt second and current seconds balance equation. You can retain is V I naught is minus of V naught by R. Same you can retain here also. IL minus V naught by R. I naught. Apply volt second equation. Now inductor volt second so in delta VL in on time plus inductor current in off time is 0. The average of inductor voltage is 0. On time is V in, say dV in, off time is Vs minus V naught to 1 minus T. Plus Vn minus dV in minus 1 minus dV naught 0. From here you can find V output is V in. This one is V in. To multiply by Vs is a Vs. Vs is V in the same. Vs divided by 1 minus T. Something if you apply a current balance, ampere balance calculation, current second balance, of capacitor IC dt plus IC 1 minus dt is equal to 0. Now this one is a minus V naught by R into T plus this one is a IL minus V naught by R into 1 minus D equal to 0. This one is cancel out. I'll find as V naught by R into 1 minus D. I can say is I naught divided by 1 minus D. In a buck converter, IL same as I naught, but in boost converter, inductor current is I naught divided by 1 minus D. inductor current same is increasing from I minimum to I by maximum. Dt total time period t. The switch Q is applied from 0 to dt on period and this one off. Then IL will charge from minimum to maximum, maximum to minimum. So I max, IL max, this one IL minimum, and this one is the average of this one, average inductor current. What is voltage appears on this VL, and switch is on. This that one, when switch is on, direct V in apply to the inductor. Say this one is V in, Vs, and switch is off, and Vs minus V naught is applied. Negative for the V output is greater than the Vs in boost converter. That's why there is negative. What is the capacitor current? When switch is on, capacitor current flow the constant output current, maintain the output current. Because I assume as output is a constant, it means output current also constant. Then IC is current flow is minus of I naught. So this one is a minus of I naught. But when switch is off, then IC current flow as IL minus of I naught. So IC is IL minus I naught. This one is IL current. I naught you can say as assume as a continuous, take as output is just constant, it means current also constant. So you minus this one IL minus of I naught, then you could say that the capacitor current goes like that, this IL minus I naught is 0 or not 0 depending on the ripple of the inductor current. And what is the delta IL, ripple inductor current? Ripple inductor current same as integration from when switch is on, inductor current same as our input current, input voltage, sorry, inductor voltage same as the input voltage. Inductor current is written as a delta IL by dt, dI by dt, Vs, DIL, Vs by L into dt. Integrate this one from I minimum to I maximum. This one is integrate from 0 to dt. Then we'll find I maximum minus I minimum is equal to Vs into dt divided by L. The I maximum minus I minimum is a delta IL. Delta IL is Vs into d, take a d if T 1 by F FL. Ripple of inductor current dVs divided by FL. What is the delta Vc? Ripple in capacitor voltage. Delta Vc same as Q is equal to Cv, then take as a average charge, average change in charge, and delta Vc is written as delta Q by C. Average charge, it means from can take as a charging or discharging current. Here is take as a discharging current is simple. Average of this one, average of this one is a Q. And what is the average of this one? A square wave flowing from a time period of dt. So I naught, the average is I naught into dt divided by total time period. Time period cancel out, I naught into d is the average of this one. And what will be the total charge? dq by dt is equal to a current of IC. Then q is integration of 0 to dt of IC into dt. To integrate this one, IC is a constant I naught, and you find I naught into dt is total charge. I naught into dt total charge. Delta is a change in the charge, or discharging time or charging time, divided by C. This means delta Vc are a change in capacitor voltage. So di naught divided by Fc. Boundary condition also here. Continuous or discontinuous conduction. Same we can take one.
Sir,
Yeah.
sir, in that previous equation, this T won't come, right? Oh, you have not written. Sir, this T,
This
because
one,
del Q is just I naught into D, right? Because T cancels out.
no, this one is a total charge, not average of this one. This one is different one. If a current, this one is a total charge, it means area of this one.
Okay.
If you take a total charge, it means area of this curve. If you take an average of this one, average it is like this. This one is the average of this. If
Okay,
you
sir,
take a T,
that is I naught into D, right?
I naught into dt, I naught current into what time is charge.
Okay.
Is the total charge.
Okay.
Current flow what time? The like this one. dq by dt, if you take a total charge, it means integration of current. Integration of any current is the area of curve. Area of curve is like this one, magnitude into multiply by the time period.
This is FC, right? On the denominator, del Vc is delta I naught by FC.
Yeah. This one T is the 1 by F, na?
No, sir. This L will not come, right? It will be C.
Oh, yeah. This one C. In continuous conduction, in boundary condition, this one is IL, same as dt, T, time period. Same way you can say IL as delta IL by D by 2. Then here the IL is different. IL I find IL like this one, V naught by R 1 minus D, and put a value here, V naught by R into 1 minus D. Delta IL, I already find this one, Vs into D divided by 2 FL. V naught is written as Vs divided by 1 minus D. It means this one is a square of ds into D divided by 2 FL. Vs cancel out. 2 FL by R is equal to D into 1 minus D of square. This one is the condition of continuous or discontinuous condition. If you take this one K, this one is a critical condition of duty ratio. The same you can say K, if K less than KCR, it's been discontinuous conduction. K is greater than KC, critical value of duty cycle. This one is the continuous conduction, and if K is same as a KCR, this one boundary condition of conduction.
Sir,
Yeah,
without rearranging and arriving at this final equation 2FL by R equal to D into 1 minus D square,
yeah,
if you stay with the previous equation, that Vs by R into 1 minus D square equal to Vs into D by, yeah, that equation, then this relation will become K greater than Kr, right? For DCM, it will become K greater than Kr.
yeah. But you can take na D is here also, here also.
Okay.
You can separate this one na, duty cycle, because all of value depending on the duty cycle. If a value of this one is less, then we increase the duty cycle. This will give us the continuous conduction. Other thing, if your duty cycle is fixed and inductor value is less, then increase the frequency. If you increase the frequency, then it is also in continuous conduction. Then what is in this continuous conduction mode, what is the voltage? Okay, same expression like this one, dt, this one as a beta t, this one t. When switch is on, then appear as Vs by L into T. I will retain here voltage of inductor voltage. Switch is on, then appear as Vs, and switch is off, appear as Vs minus V naught. Remaining time is 0. The same as apply a Bolt second balance. You can say Bolt second balance or flux balance. As same as in capacitor, current seconds or charge balance. Bolt seconds means flux balance of inductor. VL into dt plus VL into beta minus dt plus VL into 1 minus beta into t equal to 0. Here VL is Vs into t plus here is Vs minus V naught to beta minus d is 0. That time current is 0 and voltage also 0. Vs into t plus beta Vs minus dVs minus V naught beta d minus d is equal to 0. Vs dVs cancel out. Output voltage is beta Vs divided by beta minus d. Output voltage of a boost converter at discontinuous conduction mode. come in the questions. What is about this? Question is given, input voltage varies between 20 volt to 30 volt. Vs is 20 to 30 volt. Output voltage is constant 48 volt. And resistance also given 12 ohm, and find I naught V naught by R as 4 ampere. Frequency is given 100 kilohertz. The value of inductance required to limit the maximum allowable inductor current ripple is 10%. When delta IL is equal to 10% of IL is a condition. You know about the delta IL for boost converter is dVs divided by FL. Vs written as d 1 minus d V naught, because of V naught is in continuous conduction mode, V naught is Vs 1 minus d, then Vs is 1 minus d into V naught. Then divide by IL in both sides. If you take this one, d 1 minus d V naught by FL into IL, because of this one is given as 10%. Delta IL of divided by IL is 10%. And IL I find from the current second balance equation. Here V naught by R into 1 minus d. V naught by R means R goes to numerator, 1 minus d. V naught cancel out. D 1 minus d square into R divided by FL. R divided by FL. This one is high when the D is minimum, and due to ratio is minimum, that time delta IL is the maximum, and this one maximum is 10% of IL. Written as D, then find a delta minimum. Minimum means when to express as a V output is Vs 1 minus d, and find the value of d here, V naught minus d V naught equal to B, then d is equal to V output minus Vs divided by V naught, and d minimum means Vs is a maximum. Then what is the d minimum? Output voltage is given 48 volt, Vs maximum is given 20 to 30 volt, 20 to 30 volt, maximum input voltage is 30 volt divided by 48, so find 0.375. This function is given 0.1. This one is 10% of IL, it means 0.1. Then find inductor here 0.375 to 1 minus 0.375 square into 12 divided frequency I think given 100 kilohertz into 0.1 is the delta. Calculate this one, find 175.78 microhenry. You can apply here for find delta IL maximum dy by dt formula, like di by dt, dy by dt is maximum when d is respect to d, delta IL, integrate this one with respect to d to cycle of this one, then we find like duty cycle is 0.33 something, but in this converter 0.33 is not possible because of the minimum duty ratio is 0.375 to maintain the output voltage 48 volt. Mathematically this one is a 0.33 is the minimum duty ratio for the delta IL maximum, but in this converter to maintain the 48 volt the duty ratio minimum is 0.375, then take this one 0.375 not a 0.33. Next question, taking the ideal DC-DC converter is shown in the figure where all losses may be ignored. It means this all of component is ideal. The consider T is the duty ratio and T is the time period, switching time period. Then the critical value of the load resistance is RC. Critical value means the boundary condition of inductor current, and DC conversion ratio V output by V minimum, the magnitude of this one asking when operating in the discontinuous conduction mode. This one is a critical conduction and this one is a discontinuous conduction. And what is the value of RC and V output by V minimum? First of all, know about the buck boost converter. This one is a buck boost converter. So Bs inductor current inductor, so B Q D. So depending on the symbol, what we taking this one difference. For this one, if you take this type voltage of output, it means you find output voltage in negative because of inductor current flow like this type in buck boost converter. If this one flow like that, then take as the difference this one plus this one minus to find output in positive buck boost converter. This one current flow like that toward because of a diode. This one is current flow IC capacitor charge like that. Take as a condition of switch is on and switch is off. If you connect this one switch, Vs appears at the terminal here, inductor. This one is a reverse bias, Vs directed as a Vs, and this one take as output because of this one positive negative. Then what will the IC current flow like this in negative of I naught, which is on minus I naught, says the output. When Q is off condition, this is open, then remaining energy of inductor release from here to here, like that, charge the capacitor and deliver to the power to output also. That time VL is negative of VS. This one is on period, and this time there is this time is connected here, minus of V naught. Then IC is same as IL minus I naught because of same current flow here. IL current flow, IL minus V naught by R. If you find these two equations, then apply the volt second and current second. Volt second valence equation, VL into dt on time plus off time is equal to 0. This one is a Vs into d plus so now minus V naught by 1 minus d is equal to 0. You can find output voltage is dVs divided by 1 minus d. If you take as this one is a positive and this one is a negative, then this one positive, this one negative, appears as a positive. This one voltage is positive, and here is positive. It means output voltage is negative. Finally, buck boost converter. Apply current second valence equation. IC into D plus IC into 1 minus dt time is equal to 0, whereas current of capacitor is 0 and switch is on time, and IC is same as a minus V naught by R into D, and off time IL minus D is equal to 0. Minus this one V naught by R plus dV naught by R is equal to 0. This one cancel out. You can find inductor current. Average inductor current is V naught by R into 1 minus D. Draw as a form.
So, sir,
Yeah.
if IL is equal to V naught divided by R into 1 minus D. So, V0 by R, we can take it I0. I0.
Same as this one. Output current.
So, I0 divided by 1 minus D, isn't it?
Yes. This one is the average current of
Average.
inductor.
Okay.
To take a inductor current like this type, I maximum, this one IL minimum, voltage appears on this. When switch is on, total Vs appears. When switch is off, then minus V naught appears.
minus V naught.
If you take I naught as a constant, I assume in this converter, about ideal converter, then you find as a capacitor current. Capacitor current is in first, when switch is on, this one is V naught by R, it was minus I naught, and then switch is off, that time IL minus V naught by R, same as the boost converter. This one is a minus I naught, this one is a I naught minus IL minus I naught. So that, you can observe here IL, we take as output current is I naught, and can observe here on the circuit, IL current flow when switch is off. Observe this one, when switch is off, IL current flow here. If you take as an average of this one, then average of inductor current is 0. When the average of inductor current is same as the average of output current. In what time? In the 1 minus dt time. It means you can say 1 minus d into IL is equal to I naught. Take as a direct of IL current, because of when switch is off, that time current average same current flow through the output, because of the average current of a capacitor is 0. That's why you can take as a same as 1 minus d into IL is equal to I naught. From here, say I naught divided by 1 minus d.
It is same as boost converter.
Yeah, same as boost converter. Then find delta IL and delta Vc. Ripple of inductor current. For calculation, this one take as a VL when switch is on, same as a Vs when switch is on. VL delta IL by dt is equal to Vs. DIL is Vs by L into dt, and to get this one I minimum to IL minimum to IL maximum. This one irrigation of 0 to dt. Then it's one IL maximum minus IL minimum is equal to Vs into dt divided by L. This one is the I delta IL equal to dVs divided by FL, same as the boost converter. Delta Vc you can same calculate one, because of this one is the same as a boost converter. Vc is delta Q by C, I naught into dt divided by C means I naught d into Fc. For a boundary condition, IL, so the average of IL same as delta IL by 2, and IL in this converter is V naught by R into 1 minus d. delta IL is dVs divided by 2 FL. V naught you can replace as a dVs divided by 1 minus d, dVs divided by R into 1 minus d square is equal to dVs divided by 2 FL. dVs cancel out, 2 FL by R is equal to 1 minus d square. This is the condition for the buck boost converter.
Sir, एक second. Can we go to previous stage? Previous step. This V0 divided by R into bracket 1 minus D is equal to dVs divided by 2FL.
Yeah, dVs divided by FL is the delta IL.
Delta L divided by 2.
Yeah, the average current of inductor, the half of the ripple current.
Okay. That is true. Okay. So 2FL by R is equal to 1 minus D bracket square.
You want to calculate this one average of boundary condition. You know about the area of this one? A triangle half into base. Base is total time period T into height. Height is delta IL.
Delta L
Divide by total time period. That's the average.
by T.
If we cancel out this one, delta IL by 2 is the IL. All of in boundary condition converter. Take average of this one is triangle. If any triangle area is the same as half into base into height.
So this condition 2FL by R is equal to 1 minus D square.
This one condition of this. If K is greater than Kc, critical condition of a duty cycle. This one is
Then
a
it is CCM.
Yeah, continuous conduction mode. K is less than Kcr. This one is discontinuous conduction mode. And K is equal to Kcr. This one is the boundary condition.
Everywhere, sir, whether it is buck boost, boost, or buck converter, this KR and KC values are different.
K is same value, but
K is same.
Kcr value is different.
2FL by R is same
Yeah.
for all converters.
Yeah.
But this KCR is different.
Yeah, Kcr is different for different converter.
Can we make the tabulation, sir, here?
Yeah.
For buck converter, what is KCR? For boost converter, what is KCR? And buck boost converter, what is KCR? The buck boost converter 1 minus D square.
Yeah, this one buck, this one boost, this one buck boost. No?
Buck boost,
Buck converter, I think D. Sorry, this one I already find this one. Question number first.
Question first.
1 minus. Yeah, this one 1 minus D only.
1 minus D in buck.
Yeah.
This KCR is 1 minus D.
1 minus D.
And for boost,
D into 1 minus D square.
D into
1 minus D square.
1 minus D square. And for buck boost,
1 minus D square.
1 minus D square.
Yeah. This one is critical value of a duty cycle converter.
Okay. It means that whether the converter is buck boost or buck boost, if it is discontinuous mode of conduction, the value doesn't depend upon duty cycle. It is all solely dependent on 2FL and R.
Yeah.
Isn't it?
Yeah.
Whatever the load is there, it depends on frequency, inductance, and load resistance.
But when D is fixed, D is fixed means the output is fixed. If you want to output is fixed, input is fixed. A constant
But that
output.
is, but sir, that is for CCM.
Yeah.
That is for CCM. But if we are not in CCM, then it doesn't depend on D.
This one is the critical condition only. If you want,
It
yeah,
isn't critical.
critical condition.
Up to
If you
critical
want,
condition, it is dependent on D. But
yeah, if
you're
this one is a
exceeding
less than, it means go to the discontinuous conduction mode. Then this analysis, whole analysis are different.
a whole analysis is different.
Yeah, the output voltage is different and the output current is different. Inductor current also different. Everything.
Different. Okay, fine, sir. Now my question is that the single controller
Yeah.
which is designed for buck, whether it is for boost or buck boost,
Yeah.
and I am operating in continuous conduction mode. Same controller compensation will is work for the CCM DCM also. Frequency compensation, whatever we have made error amplifier and compensator,
Yeah.
whether it is voltage mode or current mode, if I design a control system, control design,
Controller will work. Don't converter will work, but is depend on the inductance value. If your frequency is fixed, inductor is also fixed.
huh?
Then the converter is work as on the continuous condition or discontinuous control. It is not a
It is not, but the way it is going to control it is different thing, because
yeah.
it is dependent on load dependent now.
Load depend. If you light load is given the light load condition, and then whole of converter goes into discontinuous condition.
It's continuous mode, conduction mode. Then everything depends on R.
Yeah.
Then.
If you are less than, that means this one is greater. Less than, it means load is more, current is more, output. If you load more, if you load increases, then a whole of greater than KCR, then goes to the continuous conduction mode. If your load is decreases, if your load decreases, it means the resistance will increase.
Increase.
So this one increases, then this value is decreased. Whole of
Decreased,
value
yes.
decreases, goes to the discontinuous conduction.
This conduct.
Whole of depends on the load.
Everything depends on the load.
Yeah.
But in CCM, it doesn't depend on that much on load.
Yeah.
But,
But if you design a converter,
hmm,
first thing is determine this one.
we have to find out whether it is CCM or in DCM. We
Yeah.
have to, according to the load condition and everything, L and F also.
Yeah. Because of you design na,
Ah,
you design well, and
ah,
R is in a range
okay,
of load.
okay.
What you want to operate,
Hmm.
and duty ratio also you define determined from voltage, input voltage and output voltage.
Okay.
And that time the main affected value is inductance. What will you put the inductance? Because once you design an inductor, you can't change this one.
L and C are designed as per the requirement of delta L
Yeah,
and
delta L, delta VC.
delta VC.
Yeah.
Okay. That these are the parameters. Delta
Yeah.
L and delta IC are the uh,
But if you take
direct.
direct, you take delta L like 50% or delta L 40%, like this one. But you don't say that now if you take a 50%, this one is continuous or discontinuous.
We can't say.
Yeah, that's when you first find this critical condition.
Okay.
It means if you want to operate a converter in continuous conduction mode, then inductor should be greater than this one value.
It should be greater than
Critical value.
critical value of L.
Yeah, find here critical value inductance
Hmm.
like this R 1 minus D square divided by 2F. It should be greater than
This is for buck
continuous
boost
conduction.
for all,
Yeah, this one for buck boost.
but this is for particularly buck boost.
Buck boost. If you take a
We have to take buck
then this
between
1 minus.
for buck. What is that?
This buck 1 minus D. Same thing. Is square is not present. This
R into 1 minus D divided by twice F.
2F.
This is for buck. This is for buck boost. And for boost,
Boost for G by 1 minus D square.
R into 1 minus D square divided by 2F.
divided by 2f. Yeah, yeah. And for
Same as the buck boost, and for boost it is same.
no, this one D is different.
D is
For
different.
boost converter, D into 1 minus D square, and for buck boost 1 minus D into 1 minus D whole square. This one
Sir,
value.
sir,
Yeah,
for boost converter, the critical inductance is R D into 1 minus D squared by 2F. Is it?
yeah, yeah, yeah. Take a critical value is this one, D into 1 minus D square.
D into 1 minus D square.
Because this one is you use the frequency control. You know about the frequency control PWM, and at a constant frequency, a different variable frequency. And in latest one, the variable frequency control are coming in the market. Every researcher you work on this. If you have a load as a light load, if a converter has a light load, in that condition frequency will be increased.
Okay.
If the frequency increased, it means it goes into continuous conduction mode.
Hmm.
Or of it.
That means the control law of that PWM is AM plus FM.
Yeah.
Both.
Yes.
But nowadays they are coming like that.
Yeah, it's a frequency control.
Previous frequency always
Frequency control.
A.
Yeah, here the frequency is fixed now.
Here
Here frequency is fixed, but in that converter, frequency is not fixed. Frequency depending on the load. If
frequency dependent on load.
yeah, if load is decreases, then frequency will increase.
So the whole analysis will be different.
Like this, if you take a buck converter, say, then take a what meaning of this one discontinuous conduction. Take like this one V naught,
Sir,
this one Q. Yeah,
sir, you are talking about changing this Q frequency.
yeah, this
no.
operating frequency.
Yes, that. Okay, okay. Sir, if the output at the light load,
Yeah.
if you increase the frequency, then we can the
You-
chances of being in
And
CCM.
normally,
Yeah, goes into continuous conduction
Yes, yes.
because you can't change the inductor in if you once design a converter, you can't change the inductor value and the resistance value depending on the load. And
But
D,
if we increase
and
the-
D value is depending on the voltage, output voltage, what you want to find. You can't control the D. D only control for the regulate the output voltage at a fixed voltage. Then only you have a frequency to increase or decrease in light load condition.
normally, sir, if we increase the frequency, the DCM will go into CCM.
Yeah, yeah. And if you are converted in continuous conduction mode, if you increase the frequency, then you can find a light a small value of an inductor. The inductor is not bulky, it's very small.
Yes, yes.
If
The
you
magnetics will be smaller.
yeah, yeah,
And even we will go from DCM to CCM.
yeah.
That is also there.
Here, if you observe this one, a buck converter, I have taken like example, the buck converter of a continuous conduction mode or discontinuous conduction mode. This one is the continuous conduction mode.
Sir,
And yeah,
sir, if you increase the frequency,
yeah,
the ripple in the current will decrease.
yeah. Yes, yes.
So inductance value will increase.
No.
Right.
If you increase only one,
same frequency.
if you take a fixed inductor,
L.
if you
Okay.
inductor is fixed, then if we increase the frequency, the ripple current will be reduced. But in frequency depending on the design of inductor. If you increase the frequency at time of design, and that time inductor will be smaller. I have taken IL in three conditions.
Okay.
IL, delta IL in the continuous conduction mode, and this one discontinuous conduction mode, and another I will take IL is like this one. Know about synchronous buck converter?
sir?
Synchronous buck converter.
Synchronous buck converter.
Yeah, instead of diode, switch will be there.
Instead of a diode, you replace by the switches. No?
If we replace by the switch, then it is bidirectional current flow through the
Yeah,
switch, and
this
that
one.
is happening here, you know.
Yeah, this one.
Ah,
This one is 0 because of the diode present.
ah.
But if you diode is replaced by the switches, then this
Then
converter work as a bidirectional converter.
bidirectional converter.
You can use as a buck boost converter of this one. If you, this one is a buck converter, you can use as a boost converter from the output fed to the input power.
Output to the input.
Yeah.
Okay.
That's one 0. It means the output we want to feed the power to the input side.
Input side.
But a diode is present here. That's why
Unidirectional.
That's why this is a unidirectional.
Unidirectional.
This condition occurs where the battery charge or something, a capacitor, hybrid capacitor like this one. You charge this one and supply this one, capacitor.
That
You, in an electrical vehicle, a battery use a battery with a hybrid capacitor. Combination of battery and hybrid capacitor. Battery is the high energy devices, and capacitor is the power devices. Energy storage devices, it means high energy storage devices means you can provide energy, a higher energy at a constant load, something, a constant load, but a load is dependent on the chemical of the battery. Current is dependent on the chemical of battery, what to current provide this. But high energy, high power density, it means it can supply a current in high current at a small time. It means you know about the motor. In electrical motor, when a switch is on, at that time the starting current will take as a 5 to 6 times of load current, full load current. Observe this one.
yes, sir.
Yeah, when EV is a motor, induction motor, electrical motor is used, and a battery present, but battery has some limitation to deliver the current, because all of the lithium ion battery is used. Lithium ion battery have some BMS system, battery management system. It has own controller like overload control or underload voltage control, over voltage control, like this. And that controller is fixed to output current. If you take 5 to 6 times of full load current, it means it behave like a short circuit. It send a signal to the controller, BMS controller. It send a signal as like a short circuit, a fault condition. Then whole of the supply is stopped. To compensate this one, you use the hybrid capacitor. Hybrid capacitor is supply the huge current.
So hybrid capacitor, you mean ultra capacitor? Huh?
Yeah. You supply a huge current in a smaller time. Because of the starting current taking very small time, 1 or 2 seconds in maximum. At that time capacitor will supply the current, whole current, and battery will be safe.
So here also in buck converter, can we replace this capacitor with the ultra capacitor or super capacitor? And then this can be R, in place of R, we have to place the battery.
Battery, yeah.
That is the combination.
The battery and a capacitor.
Battery and capacitor. Battery as a load and capacitor as source.
Yeah.
Sir, while we connect both capacitor and battery to for supplying any load, if you connect both the ultra capacitor and a battery,
yeah.
So at that time, how would you? Do we need to go for that interleaved fashion? Something interleaved converters?
Now, if you supply, if you connect a battery and a capacitor is both, then first operate as the capacitor, because the capacitor response time is very fast. Then the first supply the by the capacitor. After that battery come in the picture.
Yeah, but during starting, capacitor will be supplying.
Yeah, so capacitor supply the current.
Sir, I want to know how both the sources are connected to the load. Because two sources are there. Capacitor will be one source and the other one is this battery.
Yeah.
If you want to connect both the sources to the load, do we need to go for that interleaved type of connections, or?
Yeah, interleaved types connection. Both are different connections. Like a 3-port converter, like.
Oh, okay.
Find a discontinuous conduction output voltage of boost converter, buck boost converter. You can find this one or drive.
Yeah, output voltage.
Buck boost converter, same thing. You can drive like zero time period and switch is on dt, and this one is take as a beta t. So total time period. When switch is on, then Vs supply is right there. When switch is off, then minus V naught. Remaining time is 0. This one. Buck push converter same, minus of V naught. This one someone asked about the how is reverse current. We take as switches like that. This one is a negative current flow like that. We take it to and when it goes to the negative is 0. After it go to negative, because of a switch is on and this switch is not on. This one is off, but this one is continuously on time. Then current flow like this one. You charge the inductor. This one is charge the inductor. When the switch is off on this one, they supply the load. Supply to the source of the charge inductor. After that, this one supply to this one 0 to start from 0. This one is 0. After that, this one supply this like that. After they go to the input side.
So you mean to say, sir, current will not change?
The current will not change sudden change.
Even we change the switches, switch positions. Current will not change.
Then
In
like
synchronous, it is like this. Current will not change.
Current will not change. Voltage can change.
It will change only after the end of the cycle.
Yeah.
Sir,
Yeah.
Sir, can you say this again? This
sir, please describe that. Current cannot change.
So this current, how the current is fed back to the source when we have switch instead of a diode.
Yeah, but if we starting from there, here, in starting condition, this one flow like that. But in a steady state, this one is after the switch is on here, again this one on. We take a switching cycle. This one on, after that off, second switches cycle on. This cycle first goes to 0. In that time period, inductor current feed to the source, and this cycle behave like this. and this one is from the starting condition.
That is
Transient condition.
initial cycle.
Yeah, initial cycle. After that,
But
this one like
but
this.
this is steady state cycle.
Yeah,
What you are drawn after that is steady state cycle.
yes, yes.
Sir, how sir, just indicate how this negative current flows in the circuit
Circuit.
once.
Yes,
Yeah.
yes.
When this one switch is on,
Okay.
and switch is on, and here,
Yeah, positive. Yeah.
yeah, this one is equal to positive. After that, positive we go to the negative,
Ah.
and negative is still something time when switch is off, on. This one. When discharge the charge to load is charged to the inductor volt, like this one. If you once it goes to 0 first, IL 0
Okay.
in that direction
Hmm.
here. After that, this one in negative direction, load will charge the inductor, like this one.
Okay.
At end of cycle, this one, and next time a switch. This switch is on, and this switch is off.
Mm-hmm.
Then this switch on, the remaining energy of inductor energy supply to the load, like that. After that, this one supply to the here. In this cycle, then once input current supply to the inductor. I
So
understand this one?
here, because of the switch here, this capacitor supplies to the inductor.
Yeah, capacitor and have load. Yeah, this one.
Sir, in simulation, will it be seen?
Yeah, you can, but I have not simulation. You can simulate by own in MATLAB. If you want to, next session I use.
Okay.
So because since this switch allows bidirectional current flow, the switch on the before the inductor that is connected between the top rail and the bottom rail.
Yeah.
Since the switch allows bidirectional current, this is possible now.
Yes, yes.
So,
You have a MOSFET now. MOSFET have an internal body diode.
yes.
If you take a IGBT or thyristor, then this is not possible. Only this will work as a diode.
The switch should be bidirectional, then only
Yeah,
it
yeah.
is possible.
And your source also to take a behave like a sink.
Behave like a sink. Yes, yes.
It means this is.
Sir, what do you mean by that, sir? We have like sink.
No, if you here if you take a like a, if you supply DC supply, if you have a DC supply and they have not take a cannot flow the negative current to terminal. In that condition, it means
the source.
it will like behave like a sink. It means this is the battery.
The only battery can sink and source, no?
Yeah. If you
But
if you have a battery, then you apply it by
okay. But if the supply is made with some semiconductor switches and diode bridge, then it is not possible actually.
No.
Only battery we can do like that.
Yes.
So here both the switches should be bidirectional, and the source and the battery should be capable of driving, taking both the capable of flowing current in both the directions.
Yes, sir.
Okay, sir.
Like that, if you have a battery and drive a motor, if you take in positive direction, motor will run. After the computer is charged the battery, and switches this one. Yeah, if you in a regenerative mode, motor goes in the regenerative mode. Na? In that time, this source fed to the source, the battery will charge.
Okay, sir.
This one like we have like Bs into dt, volt second balance, plus d
V naught into
beta minus d into t p minus v naught
V naught.
plus 0 is equal to dBs minus V naught beta minus D is equal to 0. V naught is equal to dBs beta minus D. Output voltage of continuous discontinuous conduction. In continuous conduction, beta will be 1. This one T. I have question this one.
Okay.
Duty ratio is given D, RC find the critical value of RC. And here the notation reference will change. This one is a positive and this one is in the negative.
So they're indirectly asking what is the minimum value of RC that we can connect. Right?
Yeah. For continuous conduction or discontinuous conduction in boundary condition.
So RC is valued twice FL by R is equal to 1 minus D for buck converter.
RC,
For RC,
yeah,
this
2F,
2 FL by R is equal to 1 minus D.
yeah, right. But here is a buck boost converter. This one is square.
So in buck boost converter, that is 1 minus D bracket square. Okay.
Yeah, like this.
Twice FL by R is equal to 1
You
minus
take as
D
a frequency is below side, you take 1
to
minus D.
1 minus D
D
bracket
square.
square is equal to R. So 2FL divided by 1 minus D square is equal to R. That
Yeah,
is
this one.
isn't it? Okay.
Same.
Okay.
Goes to. I think this one.
D.
TSW is a time period.
And this V0 by V, that expression, mod of that expression.
Output voltage.
Output.
Because mod of given because of this one is notation of difference is positive minus negative. It means
that
output
is
voltage will be negative.
So V in divided by V out divided by V in.
You simply want to find a V output.
Okay.
Also find like something into Vs na. Then find V out by Vs.
V out by Vs.
Because of notation of this one plus minus, then this one come in the negative of something. That's why Q is the magnitude.
The D divided by that twice FL. This everything comes like that, no?
Yeah. Comes from there only. I
Sir?
try. Yeah.
Sir, in this question also, in question number 3,
Yeah.
this buck boost converter, the bottom rail is grounded, right?
Bottom.
This bottom rail, the bottom
one?
rail. Yes, sir.
No, this one is different for different. This one is for input ground here, output ground here. This one is a positive, na. Overall, if you take, see this one is positive, this one negative. We should apply like this. If you take a battery here, then should connect like that. So plus this one.
Yes, sir. If we connect in this polarity which you have mentioned, then it is positive voltage will come out.
Yeah. But in question is given the opposite. That's why different type of converter will come na. like a
Ah.
SEPIC converter, CHUK converter, 5-way converter. They all of voltage, output voltage, same direction, positive direction.
So they all give the top rail. So for both those converters, the bottom rail is the ground for both the input and output.
Yeah. SEPIC, CHUK converter, and no. CHUK converter has the same.
Yeah,
This
negative.
one positive, this one negative. SEPIC is a positive, negative, and 5-way is the positive. But CHUK converter is the same polarity, like a buck boost, but here used as the coupling capacitor.
Sir, that last expression I didn't get this V0 by the mod of. Can we make it larger? Yes. D upon root of 2L upon, what is that?
R into switching time.
R
Yeah,
into
this one.
switching time. R into TS.
Yeah,
W.
RT, like RT, 2FL by R. Remains same.
2FL by R same है. Okay. Same na?
D divided by 2FL by R.
2FL by R.
Yeah.
Okay.
You can do by one or I do.
That is boundary condition.
Yeah.
Boundary.
So this discontinuous condition, not a boundary.
This boundary, no, not this. Okay.
Discontinuous condition. Once I draw, don't worry. So given a discontinuous conduction is given as like this. 0, so dt I take for simply, I take this one as a dt time period, this one d dash t, this one d double dash t, like that. I separate the data cycle. And first one I take like a beta, beta means here to here, the beta. But in this I take like by simple phi, so d dash t, d double dash t. Then same apply the whole second balance. Balance equation VL into d into dt plus VL into d dash t plus VL into d double dash t is equal to 0. VL is same V in when switch is on, it's connected like that.
V in into dt.
V in T is all of cancel out, then V into D plus when switch is off. In out condition, this one same as a V output. V output into D dash plus this one is a 0. From this you can find D dash. D dash is minus dV in divided by V naught. Here you can observe output current. What is the output current? Output current flow when switch is off. The switch is off between this one. Then output current flow like this only in this
Yes.
period only.
Yes.
Then average output current you can say like average of this one, area of this one, average
Divided
this
by
one
T.
half delta IL this one. This one is the delta IL na, height of this one. Delta IL into time T dash T divided by total time period, or finding the average value of I naught. Then I naught will be D dash delta IL by 2. If you take this one, look in this triangle. This one is the Vs by L, input V in
Sir, it is
on time.
here
Yeah.
Sir, here the average output current is average of the inductor current only in D dash T.
Yeah, only this dash because of when switch is on, then IL current flow like this one only.
Yeah, into the source.
Switch is off, then this one current flow. But here is 0, that's why I will take only this one. Only what time of current will be present.
Okay.
And second time they take this one to find the IL max. This one IL can I delta IL can I retain as a 0, this one 0, this one I max. See this one is a 0 value. If this one 0, this one I max, IL max, then delta IL will say as IL max minus 0. It will be same as the IL maxima. What is the maximum value? Same as delta IL. In this continuous conduction, what is? Then what is the delta IL? Delta IL in this converter, Vs is present when switch is on. V in into D divided by F into L, and same as the delta IL max. Sorry, delta IL same as the IL max. And what is the IL max here? I naught is equal to D dash into IL max divided by 2, because the delta IL is same as the IL maximum current.
Yes.
You can take a V naught as a output voltage, output by R, and D dash is putting from here, this one minus D V in divided by V output into IL maximum. IL maximum can put from here, V in into D divided by FL, 2FL. All of you understand this one?
Yes. Sir, what we are trying to do?
I'm trying to find this one, V output by V.
Okay.
This one V naught, this one V naught multiplied by this one, then V naught by square. This one V in multiplied by this one and taking the cover denominator of left side. This one V in square. So, okay.
Okay, sir.
Then what will be? This one is the D square minus D square, and R multiplied by this one into R divided by 2FL.
Okay. It is D into 2F.
V naught divided by V in is equal to, if you take as a mod of this one, negative will be out of side. Then if you take a root, then D will be remaining here, and R should be R goes to the denominator of FL. You take a denominator, then 2 F is take as a R T, R into T, this one root of T is a TSW, I would can like this. So okay. First one of all, find average, apply a bold second balance equation, find D dash, this one. After then take it output current. Output current is the same as the inductor current in the off time. Then find the average of this one. Average of this one, it means area of this one divided by the total time period. Of anything, if you take the average of our form, then find the area of this one divided by total time period. The area of a triangle is a half this height divided by total time period. You find I naught is V naught by R, and delta IL is same as IL maximum. And the discontinuous conduction is present in converter. Discontinuous conduction or in boundary condition also, delta IL is same as the IL maximum, because we are starting from the 0 to IL max. I take one question from the forward converter. The forward converter primary inside turn ratio of transformer is NP and the magnetizing winding is ND, and I have a 50 turns each. It means both are same.
Yeah, understood.
One and the 200 DC voltage applied to the converter has 10% of ripple. 10% ripple means 10% varies from 180 to 220 volt input side. First we'll try a forward converter. This one supply voltage.
So 10% ripple means it is 190 to 210, right? Only 20.
10% of 20 na 20 it means 180 na
180 and 220.
180 and 220.
Yeah, no, it is a ripple. So a del IL is 20 volts.
And this
So
one
it
not
is-
a del IL.
no, sorry. Delta is 10% of 200 is 20. So total it is 20 only. So
Yeah.
it can swing from a minus 10 to plus 10 only. So it is 190
No,
to 210.
minus 20 to plus 20 because of 200 here na. 10% of 200
10% of 200.
into 10 divided by 100
So
is
20 plus minus 20.
Yeah, you can say like
No,
point,
sir, that's all. This
point
20, I got it, sir.
90% to 110% you can say total value. Up total value about 10% ripple, it means 90% to 110%.
110%.
Then apply 90% up to 100. Yeah, divide by 100 to 110 up 200 divided by 100.
Okay.
This one is 180 volt to this one 220 volt.
Sir, 10% ripple doesn't mean this much. 10% ripple is plus minus
10%.
10% plus minus, not plus minus. It is total 10%.
Yeah, total from minus del L, that is some minimum current to maximum current is 10%.
Ah,
Yeah, you can say like that. Okay.
the ripple is 10%. He has not mentioned the plus minus 10%. He has only said 10%.
Yeah, 10% to hottest value. If you take like this one, na,
Yes, sir. The average is 200.
this average is 200, and this one is totally 10%.
Hmm.
Yeah, you can say like a minimum value is
190.
200 into delta L by 200 minus delta L by 2
Hmm.
to 200 plus delta L by 2.
Yes.
I think this one forget to mention a plus minus 10%.
Yes.
Yeah.
If he has
Yeah.
forgotten plus minus 10%, then we have to take like that.
Like that is okay. If you take this one, then I think 190
190 to 210.
Yeah.
210.
So, so the simple forward converter. So magnetizing winding is a transformer. You can say okay, this one the turn ratio is given is the magnetizing winding. This one
The diode should be connected above the switch.
no this one you can say. This one a dot combination is same as input output, but in tertiary winding is opposite. This one
No,
is
sir. When switch is off, this primary winding should that flux, it should weaken, the flux should reduce, no? So diode should be connected above the switch. The anode of the diode should be connected above the switch.
here.
No, yes, sir. On the primary side, that
No,
ND,
three
the
winding is
demat-
present here, not two winding.
yes, sir. Yes, sir. That demagnetizing winding, in series the demagnetizing winding, there is a diode.
Yeah, this one demagnetizing have a diode.
That diode, okay.
Wait. Once the switch is on, na, this one is appear as a Vs here. This
Yes,
one plus minus, this one plus is coming here plus, this one minus, this dot plus, it means this one plus, this one minus. The diode will be reverse bias.
okay.
The current will not flow here, but this current is flow because of positive connected to the diode. Then it will behave like a voltage buck converter, and then output voltage is Vs of this one into Ns divided by Np.
Yes, sir.
This voltage up here, this one is VL, this one is a plus minus V out. Once this switch is off,
Oh, this is not that passive flux signal. This is something.
when switch is off, in that condition, transformer have reversed the polarity.
Yes,
This
sir.
one is positive, this one negative, this one positive, this one negative.
Yes, sir.
This one is a reverse bias, this one will forward bias, and then this one will current flow like that. And this one
Yes.
positive means this diode is positive. Oh, sorry, this one will be negative and this one will be positive.
Diode is forward bias.
Diode will be forward bias, and core is reset like this.
Yes, sir.
Input side.
Okay.
Understand this one?
Yes, sir.
Then what will be output voltage? If you find output voltage, then take a second balance of inductor. If you apply this one, then VL into dt plus VL into 1 minus dt is equal to 0. And what is the VL? When the switch is on, so this voltage minus V0, this voltage is, I will take it like as a NP by NS as a N. Okay. Then we can say this one Vs by N minus V0 into D plus minus V0. When switch is off, this one the current flow like this one, which is minus, one plus, up here is the output voltage is minus V0, 1 minus D like a buck converter. Then dVs by N minus dV0 minus V0 plus dV0 is equal to 0. dV0 cancel out, V0 is equal to dVs divided by N. I want to ask about the question is given. The output voltage is 12 volt fixed. Input voltage vary from if you take 192 to 210. Then what is the minimum possible value of secondary terms to feasible operation? Minimum value of secondary term.
We should
You
find
can
that
take
secondary voltage.
You can take like a V output is N. If you take NP by NS, then NS divided by NP into D into Vs at a minimum voltage of Vs. Na.
That is 190 volt.
You can say the maximum and the forward converter, the maximum voltage of a duty ratio is 0.5. You can't increase the duty ratio of a converter, forward converter more than 2.5. Because of this one, this turn ratio is same, ND and NP. What the voltage here, same voltage appears here. Then duty ratio depending on the magnetizing, demagnetizing voltage of the transformer. When switch is on, we take this one. If the switch is on, then magnetizing same as Vs appear on the magnetizing voltage of a transformer. Magnetizing voltage same as the input side voltage of transformer. No, magnetizing voltage inductance connected in the pillar of the
Yes, yes,
primary inductor. Then same as a Vs,
Yes.
and when this one is a reverse polarity and switch is off, and that time this one positive, this one negative, same as this one is positive, this one positive, this one negative, and same voltage appears here because of the ND same as the NP. In tertiary winding turn ratio same as the primary winding turn ratio. Then if a Vs appears on the primary winding, because diode is forward bias, the same voltage appears here. Tertiary winding, because of turn ratio is same, then input side voltage is same as tertiary winding voltage. Like magnetizing voltage is same as minus Vs. Then you can take as a Vm. If you apply volt second balance, it will be important thing. Volt second should be balanced. Flux should be balanced in any converter. If flux will not balance, that means the converter will not work.
So in the transformer also.
Yeah, transformer also. Because I would use a transformer in DC, not a AC signal. It's not a AC source, it's a DC source. To take a DC source, apply a transformer, then it will work in such condition. Then its flux should be maintained in a range. Its flux should be balanced. Flux balance means volt a second will be balanced. If you charge if you charge some flux charge, then same charge it will be same flux will be discharged in off time period. And the Vm into dt plus Vm into 1 minus dt. Sorry, this one is appears the okay. Vm is same as Vs dt plus Vm is minus Vs because of tertiary winding. This one 1 minus d into t, t cancel out, can take a common and go to 0, goes to 0. Then dVs minus Vs plus dVs is equal to 0. Then what will be d? You can take as a d maximum also. Sorry, this one not a V, you know how to quote it. This one Vs.
Yes.
This one I think 1 by 2. No, take this one. This one is 2 dBs is equal to Vs. Then d is maximum is will be 1 by 2. Maximum due to cycle of forward converter is 0.5 only. You can't increase this one. If you increase this one, it will, the flux will not be balanced. Our transformer goes to the saturation.
Sir?
Yeah.
Sir, in this winding, the primary and secondary winding, sorry, primary and tertiary winding.
Yes.
In that, each winding will have a magnetizing inductance in parallel. How we should consider that?
No, this one is transformer. Whole transformer have one magnetizing winding. This one is transformer. Have one transformer core have 3 winding.
Yeah. So if we have one primary and one secondary, then we have
like this one. This one I have transformer. I have this one primary. Sorry. And this one is secondary. And like this one is tertiary. At one core. Vs, V output, secondary, Vp, Vs, and demagnetizing winding. Then at our transformer have only one magnetizing inductance, because of magnetizing inductance depend on the
produce the
core,
flux.
only core. It affected only a core.
Okay.
Denoted by the only core. Magnetizing winding denotes like how much flux will be take to energize the transformer core.
Okay, understood.
In starting transformer core have energized by what value of flux. if a flux is denoted in the inductance. That's why this is only one magnetizing inductance.
Okay.
If you take a D maximum is a 0.5, this one is a fixed 2.5, this one also fixed, output voltage is 12. Okay, Vs will be, it means Vs in such that the Vs, if you apply a minimum voltage of input voltage, reliable is given, it's a feasible operation. Feasible operation means the minimum input voltage apply, then the output voltage also a regulated voltage at 12 volt.
12 volt.
You will find the 12 volt at output. Then what value you have? Ns. Then you can find V out will 12, Np is given 50, Ns you have find, D is 0.5, V minimum is 190, then find the Ls value. So 600 divided by 0.5, I can take 0.8, 0.5 into 190. This one I think approx 6.315. It means you have to take a 7 as a turn ratio. You can decrease this one over to 6. You have to take a 7 more than this integer value.
No, this is not turns rate here, no sir. This is NS, number of turns.
Yeah, number of turns in integer value only, na. How much turn you take?
Sir?
Yeah.
Sir, here you have defined that NS by NP is the turns ratio.
Yeah.
Similarly, the opposite terms NP by NS can also be defined as N.
Yeah. You can take this.
Sir, is there any method? No. Is there any rule by which we need to select this, or whether it is NS by NP or NP by NS? On what basis we select this ratio as N? Or reversing that, will it behave differently?
No, there is no standard rule, but you will always take as a primary to secondary as a reference. Reference. You take a NP to NS. But in every question it will mention. If you turn ratio is given like 10, 5, 12, it will mention. And what will primary to secondary, the secondary to primary, mention in every question.
So they mention.
Yeah. Without mention, you can't take a hot value.
But ratio, if you take differently, it will arrive at different answer.
Yeah. Second question is, what will the voltage stress occurs on the switches? The switch is off, like this one. At time of switching, this one voltage is negative, this one positive. Then this one voltage are same appears here also. No, negative, this one positive. Yeah, you can take this one as a VQ, as a switch voltage. Then apply a KVL here in this loop. I take here. Then what is this one? This one Vs. Or this tertiary wire is tightly connected to the Vs input side voltage. Then Vs is this only voltage is Vs at the time of starting of decreasing magnetizing current. Then same Vs apply here also. Then this one value is also Vs minus Vs plus Vq is equal to 0. Then maximum value of switch stresses on switches twice of Vs and a forward converter, single switches.
Sir, actually, across the inductor, when we are switching, there will be a spike in the voltage, right? Some small spike will be there.
Yeah, these are depending on the leakage inductance. Here I will not consider the leakage inductance. If you have a leakage inductance, then the spike comes. But in ideal condition, I have taken this one all of thing. In the ideal condition, then this was not so here. But in practical cases, some as a leakage inductance occurs here, and type of switches, the spike will come. Spike is a
So
huge spike.
can we take leakage inductance as 10% of the main inductance?
Yeah, 10%. Yeah,
Normally,
normally 10%.
Sir,
10%
why?
of magnetizing inductance.
Yeah. But again, the magnetizing till the primary leakage.
Primary
Primary
inductance.
inductance.
Primary. LP.
Yeah.
Sir,
Yeah.
since these two inductors are in series, actually in the way you have drawn, how does the leakage inductance alone contribute to the spike and this one doesn't contribute to the spike? The other one on the red.
Here.
Yes, sir. We have drawn two inductance in series, and the inductor in the black is the leakage inductance, and this is a magnetizing inductance. Sorry, and the red one with the dot.
Yeah. Yeah.
Reset
So
winding.
yes, sir, reset winding. So if we, how we can, how we are saying that the spike is only on the leakage because same almost same current will flow through both the things. Actually, this usually in the equivalent circuit of the transformer, this leakage inductance will be in series with the source.
Yes. 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 This one is the
Uh,
same as the series in only.
yes, yes, same. But sir, can you say how this one, how the voltage reversal in the leakage inductance
This
contribute to the spike?
primary in the primary turns are winded with bifilar winding, and then isolation, and then secondary is wounded.
Both are
So
bonded in the in one leg of the
one
spike.
leg.
If you have
So there is
this
a
one,
leakage inductance between secondary and primary. But in primary and reset winding, there will be no leakage as such because it is wounded like that only.
no, I this one the leakage inductance taken as a equivalent leakage inductance, primary,
Yes,
secondary both.
yeah. Primary, secondary both.
Yeah,
Yes,
secondary times secondary side is very less number of turns.
turns.
If you
It is
take a
quite
very less number of turns, then the leakage inductance also very less.
very less.
But this one, if you take like inductance, leakage inductance, you show here, this means it means leakage inductance of equivalent leakage inductance of the whole transformer, not a primary winding, a secondary winding, will the whole transfer to the primary. Is okay?
Okay.
Yes.
Okay, I am stopping here. Try to.
Thank you, sir. Good night.
Sir,
Yes.
here worst case stress will be 210 plus 210 that
210
plus 210 volt, that is 420 volt.
maximum stress, na?
Maximum stress,
Yeah,
yes.
yeah, yeah. In ideal cases. To reduce the stresses on the switches, we use the two switch forward converter. One other
Ah,
switches are used here.
okay.
And two switch forward converter. This one also, this will not.
Reset winding is
This
not
advantage is not needed. And leakage effect also reduced.
yes.
Into switch because of when just switch is off, then same current flow through the diode in same winding. Okay, everyone.